Section 2.7 talks about differentiation formulas. In this section, we're going to learn the chain rule, which is a rule that you're going to apply on every derivative that you will ever come across. And this is what it's trying to do. You're trying to take a derivative of two functions embedded within each other. So you have a function within a function. The goal is to pick g of x and then separate those two. Have g of x be a function and f be a different function. And the shortcut, and I'm going to go over that with you, turns out to be when you want to take a derivative, you take the derivative of the outsidemost function times the derivative of the inside function. So you just have to kind of pick it up. The tricky part is picking u and letting that be g of x. And if I take the yellow out and put a u in there, you'll notice that the function f now will depend on u. And when you take dy dx, we're going to say now y depend on u, and by the chain rule, u depend on x. Those two need to match, because you could cancel that at any time and end up with a dy dx. So here are three functions that I want to take a derivative of. And I notice I know how to take a derivative of x squared plus 3x plus 1. I know how to take a derivative of a quantity to the third power, but I don't know how to take a derivative of those two embedded within each other. So I'll go on the side and I'll say, so u is going to be the inside of a power function, the inside of a radical, a quantity that you could take out and change the nature of the problem to really two functions embedded within each other. So if I let u equal x squared plus 3x plus 1, then y is going to equal u cubed. The deal is, I know how to take a derivative of u cubed, and I know how to take a derivative of x squared plus 3x plus 1. And to find dy dx. Now, dy dx is Leibniz notation. Newton used f prime. Leibniz used dy dx, and this allows you to say, well, y now no longer depend on x. This is like the middle step. Y really depend on u, and automatically whatever this is, this have to match, and u depend on, and if you look at u, u depend on x. And in this case, we'll say dy dx equal, now the derivative of u to the third with respect to u, bring the power down, subtract 1 from the power, and the derivative of u with respect to x is 2x plus 3. So this process allows me to take a derivative of a function embedded within another function. The catch, you need to replace u back, and if you remember, u was x squared plus 3x plus 1. And by doing that, you are able to take a derivative of the two functions embedded within each other. So I look at the second problem, the same deal. I'm going to go ahead and let u equal the inside of a power function, the inside of a radical, the denominator of a fraction later on. So if I let u equal x to the fifth plus 1, automatically that makes this a u to the 100. Excuse me, y will equal that. And now when I say find dy dx, you'll say, well, let's see. Y depend on u, and automatically u depend on x. So now I could say dy dx, the derivative of this function, u to the 100, with respect to u, you bring the power down, subtract 1 from the power, times the derivative of u with respect to x, that's 5x to the 4th. And again, the catch is you need to get rid of u because it wasn't part of the problem. You added that into the problem so that you can take a derivative or differentiate. And what's u? u was x to the 5th plus 1. And by doing this trick, you are able to take a derivative of a function that initially you couldn't. And if I get to the third function, I'm going to let u equal 2x squared plus 5. That makes y equal u to the negative 4. So dy dx, and by now hopefully this is becoming a bit simpler. Y depend on u, and automatically u depend on x. So dy dx, the derivative of this power function, bring the power down, subtract 1 from the power, times the derivative of u with respect to x is 4x. And if I replace u by what it equals, I'm really looking at negative 4 times negative 4, that's 16, u to the negative 5 times x, and u was 2x squared plus 5. Actually, I wanted to leave those as they are for a reason. And now, if I look back at this, you'll notice I'm taking the derivative of the outsidemost function times the derivative of the inside. So if I glance at this, the shortcut to eliminate these steps, take a derivative. If you ignore the yellow part, look at the outsidemost function, that's a cubic. You bring the power down, subtract 1 from the power, and copy this, that should be a 1 there, times the derivative of the inside, and that's where the word chain comes from, the chain rule. Derivative of x squared plus 3x plus 1 is 2x plus 3. Same deal here. If I eliminate these steps, so I could write that, but just to save time, eliminate all of these. Bring the power down, subtract 1 from the power, leave the inside alone, times the derivative of x to the 5th plus 1, which is 5x to the 4th. And if I want to eliminate those, the same deal happens here. I want to take a derivative. The outsidemost function is raised to the negative 4 power. You bring that power down, and you subtract 1 from the power, times the derivative of the inside, which is 4x. Of course, you could simplify that after, but I just wanted to point out what we're doing. So the chain rule is a rule that you're going to apply on every derivative you take from now on. If I want to take a derivative of this, of course I could let u equal this, or I could simply say, you know what, the outsidemost function is to the 10th power, so dy dx is bring the power down, subtract 1 from the power, times the derivative of the inside function, which is 5x to the 4th plus 8x. And that's pretty much it. Now if I get to b, I'm going to take a derivative of this, bring the power down, subtract 1 from the power, times the derivative of the inside, which is the quotient rule. Derivative of the top times the denominator, minus the top times derivative of the denominator, all over the denominator squared. Now on a test, this is all I want. For the homework, you're going to clean that up. And you'll notice this is going to be 4 times x squared plus 1 cubed over x cubed plus 1 cubed, but that should be squared, times this is going to be 2x to the 4th plus 2x, that's a plus 1. And here, negative 3x, x squared times x squared is negative 3x to the 4th, and negative 3x times 1, negative 3x squared, over the denominator squared. And if I clean that up fully, the top is 4 into x squared plus 1 cubed. The denominator, when you multiply those, they match. So you add the powers, and this is going to be a negative x to the 4th minus 3x squared plus 2x. And there it is. Now, if I take a derivative of f, I'm running out of space, I'm just going to make some adjustments. And now if I get to part C, if I want to take f prime, this is the product rule, derivative of the first, and again, it's worth memorizing that the derivative of the square root is 1 over twice the square root. Derivative of the first times the second plus the first. If I want to take a derivative of this, I'm going to bring the power down, subtract 1 from the power, times the derivative of this, which is 3x squared plus 2. That's a final answer for the exam. For the homework, you're going to clean that up. You're going to make the whole thing over to radical x. That's x cubed plus 2x to the 5th. And if you multiply this by 2 radical x top and bottom, you'll notice 2 times 5 is a 10. Radical x times radical x is x. And that's good enough. Now you could factor it further, but for now, let's just get this far. No, I suppose we could take it a step further, why not? F prime is, you could factor x cubed plus 2x to the 4th out. You will have out of this an x cubed plus 2x, and out of this, you took this out, you're left with (10x) times 3x squared plus 2. F prime would be x cubed plus 2x to the 4th. That's going to be 30x cubed plus x cubed is 31x cubed. 20x plus 2x is 22x, and of course you could factor an x out of both of those, but we're not going to worry about that right now. We're just going to worry about can we apply the chain rule, and that's really what counts. But on the long run, you're going to have to really clean this up as much as you can. And there it is. If I get to the next problem, I could use the quotient rule. Or I could say, you know what, I really don't need the quotient rule, because I could think of this as y equal 5 times x squared plus 3x to the negative 2. Y prime, you ignore the 5, so bring the power down, subtract 1 from the power, times the derivative of the inside. So again, now that you know about the chain rule, it's never going to leave you alone. And negative powers we move down. So if you start the problem with a negative power, supposedly you could beat the answer with negative power. But if you don't start the problem with a negative power, you have to go back and fix it. Here, if I take y prime, the product is derivative of the first times the second plus the first derivative of this. You bring the power down, subtract them from the power, times the derivative of the inside, which is a 3. Again, on the test, this is what I want. For the homework, you're going to factor the greatest common factor, which in this case, x to the 5th and x to the 4th, that's x to the 4th, and I'm going to take 3x plus 3 squared. When I take this divided by this, I'll have a 5 into x, 3x plus 3 to the 1, plus, and here, 3 times 3, that's a 9. If I take x to the 5th divided by x to the 4th, that's an x, and that cancels out because I'm factoring it out. So y prime is actually x to the 4th, 3x plus 3 squared, times 15x plus 9x is 24x, and 5 times positive 3 is 50. So anything that I'm boxing is accepted on the test. If I look at the next problem, and that's something we're going to be doing all throughout, find an equation of a tangent. Well, equation of a tangent, y minus y1 equals m into x minus x1, and what's the derivative? Y prime, which is the slope of the tangent, is 1 over twice the square root times the derivative of the inside evaluated at x equal 1. Y prime will be 3 at the top, square root of 2. You could rationalize if you wish, no need to. And that's pretty much it with this section.